Every year, over 65 million tons of goods move through the air. It is a massive, relentless flow of high-value cargo, navigating a dense web of global routes. The logistical bottleneck has moved beyond the physical movement of goods. We have already solved the physics of flight and the engineering of long-haul speed. The modern challenge is custody. It is the friction of multi-carrier handoffs and the difficulty of verifying the physical condition of a shipment as it passes through third-party warehouses, through customs checkpoints, and ocean-to-ground transfers. To move high-value freight without blind spots, the global supply chain relies on an integrated stack made up of 3 distinct layers. Layer 1 is the hardware, standardized physical modules that act as the building blocks of transit. Layer 2 consists of the network nodes, the multimodal superhubs that consolidate and distribute this cargo at an industrial scale. And Layer 3 is the nervous system, continuous digital telemetry that monitors the cargo's condition from the inside out. Mastering all 3 layers of this stack allows organizations to protect sensitive freight and eliminate the physical blind spots that cost millions in losses. The foundational physical unit of air freight is the Unit Loading Device, or ULD. Air cargo follows a strict geometric hierarchy. Both the freight and the airframe are engineered to conform to the specific dimensions of the ULD. The PMC pallet, 96 by 196 inches, 11,340 kilogram limit, snaps into the lower deck contour of a wide-body fuselage alongside an AK container. The Boeing 777 freighter is entirely designed around a fully loaded grid of these standardized units. Because the interior volume is optimized for these exact shapes, the 777F carries a 102-ton payload across a 9,200-kilometer range. Geometric standardization at the pallet level is what allows airlines to load, balance, and launch hundreds of tons of freight with predictable speed. Multimodal superhubs function as centralized consolidation and redistribution engines, purpose-built for high-volume freight handling rather than passenger transit. Memphis International Airport handles roughly 4.5 million tons of freight every year as the global superhub for FedEx. Hong Kong International Airport processes 4.3 million tons annually, serving as the premier international gateway connecting half the world's population. To process these volumes, these facilities utilize millions of square feet of automated sorting systems. They are designed to break down incoming ULDs, route individual packages, and rebuild outgoing units in a matter of hours. Superhubs are the high-efficiency valves of the global supply chain, but routing cargo through them necessitates complex physical transfers. Global operations are scaling to meet the demand of cross-border e-commerce, with a new generation of specialized meganodes rising to handle the volume. China's Yizhou Huahu Airport is a primary example of a dedicated cargo meganode built from the ground up for this purpose. Its growth metrics include a 289% year-over-year increase in outbound capacity. In Europe, DHL Supply Chain is expanding its Leipzig-Halle campus to meet similar capacity requirements. This diagram shows the scale of the new 34,000 square meter Leipzig facility. It adds physical capacity for up to 55,000 pallet spaces. The capacity of the Leipzig campus is multiplied by its multimodal connections, which instantly link air freight to domestic parcel services, rail, and highway networks. As physical infrastructure scales and becomes more multimodal, it increases the number of physical handoffs between carriers. Every handoff introduces a critical vulnerability. The carrier handoff is the most significant blind spot in the entire logistics stack. The industry has historically relied on electronic data interchange portals and passive data loggers to track shipments. Milestone scans are structurally flawed for high-value freight. Batch processing creates information blackouts that can last for hours while cargo sits in customs or moves through third-party warehouses. Discovering a damaged electronics load worth hundreds of thousands of dollars only after it reaches the delivery destination means the loss has already occurred. It triggers a reactive claims process based on stale data. Knowing a shipment was scanned 6 hours ago offers no proof regarding its physical safety, its location, or its environmental condition right now. Layer 3 provides the solution through continuous digital telemetry. Companies place multi-network IoT trackers, like the Tive's Solo 5G, directly inside the cargo itself. This timeline comparison shows how tracking power moves to the shipper. These devices broadcast continuous ground truth data. For electronics, a humidity gauge maps moisture fluctuations that destroy circuit boards. If a crate drops, the tracker instantly records the exact G-force impact. Integrated light sensors act as a mid-transit alarm for unauthorized door openings, providing the exact location of a potential theft while the cargo moves. Moving from reactive carrier scans to sensor-driven telemetry allows a supply chain to proactively manage exceptions while the cargo is still recoverable. All three layers of the modern supply chain operate in unison to move goods across the planet. It starts with the geometry of the standardized unit loading device locking into the cargo hold of a Boeing 777 freighter. The aircraft feeds into the automated interchanges of a global superhub, where freight is sorted and transferred to the next mode of transport. Throughout physical movement and carrier handoffs, the digital overlay broadcasts an unbroken, real-time chain of custody. Modularity dictates speed. Superhubs deliver scale. Continuous telemetry guarantees custody. For high-value logistics, knowing cargo is in transit is an obsolete metric. Unbroken, independent ground truth verification is the new baseline standard.